So we've learned all about dot products, which of course form a scalar when you multiply two vectors. But there's another kind of multiplication with two vectors that's called a cross product, also known as a vector product, because it won't result in a scalar like the dot product did, it will result in another vector. Now, I want to drive the definition of this with a little bit of physics. So when we were doing the dot product, work was the force vector multiplied by the distance vector, right? In a dot product form. But what if instead of moving the object through a distance, instead you use the force to turn or rotate, i.e. twist the object? Well, that means we're going to need a new concept called twisting power, which is torque. Torque is the twisting power that we exert when we use our force to twist rather than to move. So imagine using a wrench to turn a bolt. So this is a wrench, and there's a bolt right here. You exert your force this way. So you have a force vector. Let me kind of put it this way. So there's your force. And then you have your radius, which is from the center of the twisting out to where you exert your force. And that's your radius vector. And then you have an angle that you're forming between your force vector and your radius vector. So you push this way, and that angle that you're forming is theta. All right, so let's define all those. Sorry, this one's getting lost in this arrow here, but there's a force vector there. Okay, so 1, the length of the wrench would be the magnitude of that radius vector. So the length of the wrench is the magnitude of your r vector. The amount of force you apply, of course, is the magnitude of this force vector right here. Here, I'll just kind of highlight it in black right there. Right, so you have your force vector right there. So the amount of force applied is the magnitude of that force vector. And the angle at which the force is applied is what theta is. And there we have it. So when we think about turning that bolt, the twisting power, is the twisting power a scalar quantity, or does it act in a specific direction? And the answer is it totally acts in a specific direction. It very much does. And you can know this if ever you try to tighten or loosen a screw. You can feel that there's an easier way and a more difficult way. And that's not just the wood. That's also the twisting power that's working down the, down the bolt, down the center line of the bolt. So that leads us to the twisting power, which is tau. Okay, so that's tau in Greek, T-A-U. It's a Greek letter T, so it has a little hook on it. So the magnitude of the tau vector is equal to the magnitude of the radius vector times the magnitude of the force vector times the sine of your angle theta. So torque, which is your twisting work, acts in the direction perpendicular to the wrench force according to the right hand rule. All right, so what do I mean by that? And this is true for like door hinges as well as, all sorts of things. So let me pause and see if I can zoom back out so you guys can see my hand. 1 second. All right, so I have a wrench now with a rather lame bolt, but it will work. Okay, so if you apply your force this direction, so if I push my hand this direction, it's going to cause the bolt to twist this way. And so the right hand rule says that the thumb, which is sticking up at the camera, hello camera, that's where the torque is going to go. The torque is going to work its way up the bolt, which when you look at how the bolt is going, right, that would be twisting it to the left. And everybody knows righty-tighty, lefty-loosey, right? Because when you're twisting this way, right-hand rule, the thumb sticks up, and that means the torque is going up the bolt, right, from the bottom of it to the top of it, which is going to loosen it, right? But if you go the other way, oops, I got to twist my hand around. Hold on. So with my right hand, if I take the bolt and I twist it this way, pushing that way, then my right hand, you can't see it, but my right hand is pointing down. So my fist is up here, my thumb is downward. Hello, my thumb. And it goes down the bolt. So that's why if you push this way, the torque, you have to have your bolt be that way. So if you push this way, your torque goes down the bolt, which is why twisting it this way tightens it, because you're driving the torque down into the wood, although I can't do that on this paper. If you go the other way, I curl my hand up or around, right? So I'd be pushing the wrench the other direction, and then the torque is going to go up the bolt because my right hand would go up like that. Hello, camera. Right, so that's how it works. So the torque goes according to the right hand rule. So you push, if you push the force, here watch, if I push the force this way, boop, like that, I'm curving and then the torque goes up. If I push my force the other way, it has to be with your right hand, no lefties allowed, then I push the force the other way, and the torque goes down the bolt because my hand curls this way and my thumb is pointing down at the paper, meaning if I twist the bolt this way, then the torque goes down. Okay? So righty-tighty, because when you when you push this direction, right, clockwise, you're driving the torque down, right? That twisting power goes down the bolt because your thumb is pointing at the ground. If you go the other way, let me turn around, then my thumb is pointing up and it twists, the torque is going up, and that would loosen the bolt. And that has to do with the way the planes are made in the screw, but nevertheless it's still true. All right, so hopefully that explains the right hand rule. It's a fascinating rule, and yes, there's tons of physics involved, and it actually works this way for like hinges and doors and such. So if you're opening a door, if you're pushing it one way, then the torque is going up the hinge. If you're pushing it the other way, then the torque is going down the hinge.